Imagine a world smaller than an atom, a world so minuscule that it defies our conventional understanding of size and scale. This is a realm where the very fabric of reality is woven from the tiniest threads imaginable. So small, it's almost impossible to imagine. Yet this is the domain that string theory seeks to explore and explain. It's a world where the usual rules of physics seem to blur, and new fascinating principles come into play. This is the realm of string theory, a groundbreaking framework in theoretical physics that proposes a radical shift in our understanding of the universe's fundamental structure. It's a radical idea, a departure from what we thought we knew about the universe. Traditional physics has long relied on the concept of point-like particles, but string theory challenges this notion. String theory says the universe isn't made of point-like particles. Instead, it suggests that the fundamental building blocks of everything are tiny, one-dimensional strings. Instead, it suggests everything is made of tiny, vibrating strings. These strings can vibrate at different frequencies, and it's these vibrations that give rise to the particles and forces we observe. These strings are so small they're far beyond our current ability to see them. Even the most powerful microscopes can't detect them, making this a purely theoretical construct for now. Think of the strings like the strings on a violin. Just as a violin string can produce different notes depending on how it vibrates, these cosmic strings can produce different particles based on their vibrations. Just like different vibrations on a violin string produce different musical notes, different vibrations of these cosmic strings create different particles. This elegant idea provides a unified way to understand the diversity of particles in the universe. This simple idea that everything is made of vibrating strings has the potential to revolutionize our understanding of the universe. It offers a new perspective on the nature of reality itself. String theory offers a way to unite the two pillars of modern physics: Einstein's theory of general relativity, which describes gravity, and quantum mechanics, which governs the microscopic world. These two theories have long been at odds, each successful in its own domain but seemingly incompatible with the other. These two theories seem incompatible, like two pieces of a puzzle that don't quite fit. General relativity works well on a large scale, describing the curvature of space-time and the motion of planets and stars. Quantum mechanics, on the other hand, excels at explaining the behavior of particles on the smallest scales. String theory attempts to bridge this gap, providing a single framework to describe all the forces and particles in the universe. By proposing that everything is made of strings, it offers a way to reconcile these two seemingly disparate theories. Join me as we journey into the heart of string theory, exploring its fundamental principles, its profound implications, and the potential it holds for unlocking the deepest secrets of the cosmos. We'll delve into the mathematics and the mysteries, seeking to understand how this theory could change our view of the universe. Along the way, we'll encounter the work of Stephen Hawking, a brilliant mind who made significant contributions to our understanding of black holes and the universe itself. His insights and discoveries continue to inspire and challenge us as we explore the frontiers of theoretical physics. Let's delve into the heart of string theory. Imagine a guitar string, pluck it, and it vibrates, creating a musical note. Now imagine that string is incredibly tiny, much smaller than even an atom. This is the basic idea behind string theory. In string theory, the fundamental building blocks of the universe aren't point-like particles, but these tiny, vibrating strings. Just like different vibrations of a guitar string create different notes, different vibrations of these cosmic strings produce different particles. An electron is one kind of vibration, a quark is another, and so on. This elegant idea has profound implications. For one, it could help us finally unify the laws of physics. Currently, we have two very successful theories: general relativity, which describes gravity, and quantum mechanics, which governs the subatomic world. However, these two theories clash when we try to combine them. String theory offers a potential solution. It suggests that gravity, and all other forces and particles, can be explained by the interactions of these vibrating strings. It's like finding a single, elegant equation that can describe the entire universe, from the smallest particles to the largest galaxies. String theory gets even more intriguing when we consider its implications for the very fabric of space and time. This theory, which aims to reconcile the seemingly incompatible realms of quantum mechanics and general relativity, suggests that the universe is far more complex than our everyday experiences might lead us to believe. We experience the world in three spatial dimensions: up-down, left-right, forward-backward, and one dimension of time. These dimensions are the stage upon which all physical phenomena play out, from the motion of planets to the interactions of subatomic particles. However, string theory suggests the existence of extra hidden dimensions. These dimensions are not immediately apparent to us, but they could be intricately woven into the very fabric of our universe, influencing the fundamental forces and particles that govern reality. Imagine a tightrope walker moving along a rope. To an observer from a distance, it appears that the walker can only move back and forth along a single line, constrained to a one-dimensional path. From a distance, it appears he can only move back and forth along a single line. This is analogous to how we perceive our three-dimensional world, seemingly limited to the dimensions we can directly observe. But an ant crawling on the rope experiences an additional dimension, the circumference of the rope. This tiny creature can move not just along the length of the rope, but also around its surface, revealing a hidden dimension that the tightrope walker cannot access. Similarly, string theory proposes that our universe may have extra dimensions curled up at incredibly small scales beyond our perception. These dimensions could be compactified, meaning they are so small that they are effectively invisible to us, yet they play a crucial role in the behavior of fundamental particles. These extra dimensions are not just a mathematical quirk, they play a crucial role in the consistency of string theory. They provide the necessary framework for the theory to function, allowing for the unification of all fundamental forces and particles in a single, coherent model. Just like the different shapes of musical instruments affect the notes they produce, the geometry of these extra dimensions determines the properties of the fundamental strings and, consequently, the particles and forces in our universe. The vibrations of these strings, influenced by the shape and size of the extra dimensions, give rise to the diverse array of particles we observe. The idea of extra dimensions might seem strange, but it's a natural consequence of trying to unify gravity with quantum mechanics. These two pillars of modern physics, which describe the large-scale structure of the universe and the behavior of the smallest particles, respectively, require a new framework to be reconciled. These extra dimensions provide the breathing room needed for the mathematics of string theory to work, offering a framework for a consistent description of all the forces of nature. By incorporating these hidden dimensions, string theory aims to bridge the gap between the macroscopic and microscopic worlds, offering a unified understanding of the cosmos. Stephen Hawking, a titan of modern physics, made groundbreaking contributions to our understanding of black holes, those enigmatic objects with gravitational pull so strong that nothing, not even light, can escape. Black holes are regions in space where the gravitational pull is so intense that it warps the fabric of space-time itself. This warping creates a point of no return, known as the event horizon, beyond which anything that crosses is lost forever to the black hole's insatiable appetite. His work intertwined deeply with string theory, a theoretical framework that attempts to reconcile quantum mechanics and general relativity by positing that the fundamental constituents of the universe are not point particles but rather one-dimensional strings. These strings vibrate at different frequencies, giving rise to the various particles and forces we observe, offering profound insights into the nature of these cosmic behemoths. Hawking's theories suggested that black holes could be described by the same principles that govern the smallest particles in the universe, bridging the gap between the macroscopic and the microscopic realms. One of Hawking's most famous discoveries was that black holes are not entirely black. Contrary to the earlier belief that nothing could escape a black hole, Hawking proposed that black holes emit a faint radiation due to quantum effects near the event horizon. He showed that they emit a faint radiation, now known as Hawking radiation, which arises from the complex interplay of quantum mechanics and gravity. Now known as Hawking radiation, due to quantum effects near the event horizon, the boundary beyond which nothing can return. This radiation is a result of virtual particles being created at the event horizon, with one particle falling into the black hole and the other escaping into space. Due to quantum effects near the event horizon, the point of no return for anything falling into a black hole. This discovery was revolutionary because it suggested that black holes could eventually evaporate over time, losing mass and energy through this radiation. The point of no return for anything falling into a black hole. The event horizon acts as a cosmic gatekeeper, dictating the fate of all matter and energy that comes too close. String theory provides a microscopic description of this radiation. It suggests that the Hawking radiation arises from the stretching and breaking of strings near the event horizon. These strings, under the immense gravitational forces, can snap, releasing energy in the form of radiation. It suggests that the Hawking radiation arises from the stretching and breaking of strings near the event horizon. This process is akin to the vibrations of a musical instrument, where the string's tension and frequency determine the sound produced. Think of the event horizon as a vibrating membrane. As strings approach it, they can get caught and stretched, eventually breaking apart, with some of the broken pieces escaping as Hawking radiation. This analogy helps to visualize the complex interactions at play in these extreme environments. As strings approach it, they can get caught and stretched, eventually breaking apart, with some of the broken pieces escaping as Hawking radiation. This process not only provides a mechanism for black hole radiation, but also offers a glimpse into the fundamental workings of the universe. With some of the broken pieces escaping as Hawking radiation, this radiation is a testament to the intricate dance between gravity and quantum mechanics, revealing the hidden symphony of the cosmos. Hawking's work on black holes and string theory helped to illuminate the deep connection between gravity, quantum mechanics, and thermodynamics, the study of heat and energy. His theory suggested that black holes could be understood through the lens of thermodynamics with properties such as temperature and entropy, the study of heat and energy. This connection has profound implications for our understanding of the universe, suggesting that the same principles that govern everyday phenomena also apply to the most extreme conditions in the cosmos. His insights continue to inspire physicists to this day, pushing the boundaries of our understanding of the universe's most extreme environments. Researchers are building on Hawking's legacy, exploring new theories and conducting experiments to test the limits of our knowledge, pushing the boundaries of our understanding of the universe's most extreme environments. The quest to understand black holes and the fundamental nature of reality continues, driven by the pioneering work of Stephen Hawking and the ongoing efforts of the scientific community.